herself to you. She is a former SPD school student, right? She's from mechanical engineer. She works in the area of minimal invasive surgery. And by the way, when I was a student, I tried to work in this area. This is very interesting area, but not easy. So you got what I am saying? So, and I know from your bio sketches that you already have a company, your own company, yes?
Yes.
So again, she's a very good example. If someone like start his or her startup company, this is maybe the good model that you can follow Dr. Maria. So welcome and feel free to start your presentation.
All right, thank you. So yes, I had asked who would work for Ethicon Endosurgery. That's where I did my co-ops as a mechanical engineer, but there were also bioengineering students. So I just got extremely interested in that area. So this is advice just in general for if you're looking for research areas or interested in pursuing a thesis or dissertation, is use what you know. If you know something already, like if you have some knowledge in a particular area where there's also a need, capitalize on that. I had already done some work in the design of the two types of devices that I researched. So I already had an advantage from the start. I had some background in that area and applied that. And I mean, anything that you can apply that you already know is going to speed up the process of all your background research that you have to do. So just throwing that out there. Always use your strengths. Use stuff from your experiences that you have with your co-ops and see if there's a need. See if there's advisors here that also do work in those areas. So I did work in minimally invasive surgical devices. And what I did overall is I took design theory, which that's the whole thing in the mechanical engineering department, and I crossed that with surgical devices. So I loved bioengineering, kind of wish I would have gone that route, but I was still able to go that direction while also using my mechanical knowledge. So we'll get into this. I plan on doing a big background for you guys so that you can get an idea more so of what this whole area is about. And then I'm going to tell you my specific research project about my dissertation and my research tasks. Then I'll spend some time on future work, because I would really love to give you all some ideas if you're interested in the area. So minimally invasive surgery, what is this? It's really where they're not going to completely open you up, but they're instead going to make very small incisions. And they will either use a trocar, which you can see up at the top. Those are devices inserted through a trocar through the incision. Or sometimes they will take the device and directly go through the incision. So either way, just to access. So what this does, you have a way shorter recovery time. You know, your scars and your wounds, they're so much smaller. Just in general, it's so much better for the patient, as well as way less risk in terms of infections and many different types of things that you can have when you're opening a bigger portion and exposing more to the environment. Yes, like that. Yeah, so it's used to explore, remove, or repair internal elements. So multiple applications in this area. So there has to be specific devices for this procedure type. They can't just be the traditional instruments. And as you see in these two pictures, what they're going to do, they're going to have a long shaft from the actual handle of a device in most of the cases. And that's so that you can go through the small incisions but still do everything that you need to do. These were the two that I investigated. You have the endoscopic stapler, that's on the left, and then you have an energy-based tissue sealer on the right. So these are very complex instruments. The endoscopic stapler, some are purely mechanical, but then actually now they're getting into powered devices as well, where they're battery operated and they actually will fire the device for you. So they'll cut and staple tissue for you, because the force to fire with the hand, it can be quite difficult. Let's say if you're on stomach tissue or even some diseased lung of some type that you're removing, not so easy to cut through and staple and get through. The tissue sealers, those are more for smaller tissues and organs and things, mostly vessels. So they will cut and seal vessels as well as they can create tissue planes for you. So that's where the distal tip there, the jaw, is heated up in order to do that. Yeah, so those are just some examples. Many different types of procedures are now laparoscopic or minimally invasive, either term for that. Oh, also, I wish I had these devices for you, but for my research, I had to literally take them apart. So they're in pieces, sorry. Because it's good to see them. But I'll give you a more in-depth overview of these. This is the stapling devices. So this isn't up close. That's the full device up at the top. So you have this long jaw at the end, and what it's going to do is it's going to clamp on whatever tissue that's the target tissue. It could be, like I said, lung, bowel, stomach, whatever the case. And it's going to simultaneously fire a knife through the middle and create staples on the side. So literally, like you just have a stapler and you staple, really will be like those B shapes. They are investigating different shapes in order to create a better seal, but in general, lots of them have literally a B-shaped staple. They're just very tiny titanium staples. And this is more for bigger tissues, like I mentioned, versus the other device we'll get into. So in the middle here, you've got a knife going through the middle, and on both sides, you'll have the staple. So this driver here, it's actually a mechanism. So here's the knife here, and then here's a portion of it driving the knife. Same portion driving the knife is going to drive these, literally they're called drivers, and push up and form staples on the top over here. Can't see, it's hard with the quality, but there's little pockets in there, like little staple pockets to form those, so a bunch of small ones. The energy-based devices, they are, in my opinion, they were a little more complex because you're dealing with power, energy, electrical stuff. As a mechanical, that was, a little more foreign to me, but it's really interesting. They'll either utilize bipolar, where they're actually transferring current through the tissue. So you're going to clamp onto a vessel, let's say, and a bipolar device is going to create the seal by actually delivering electrical energy from the bottom jaw up to the top, or whichever way it's designed. So it's transferring that energy through the tissue to create a seal. Those actually have to have a knife as well. Bipolar technology cannot cut tissue and seal it at the same time. So electrical energy creates the heat to seal, and then you have to have an external knife component to come through and actually make the cut. The other type of device is ultrasonic technology. So that's ultrasonic vibrations. And that actually can create a cut and a seal simultaneously. And actually you can, different settings on the device, you can actually just seal or seal and cut. So it's a lot of versatility there. There's one device that was relatively recently released. That's lots of R's there. But it actually has bipolar and ultrasonic technology integrated into this same device. So that's a newer one, and I was able to get a hold of one of those devices to tear that sucker apart. So the motivation behind this, it really comes down to that there are problems and we need to fix the problems, right? General engineer issues going on. Any type of a device, mechanical, anything like that, it has the potential to fail. And even though it may be a relatively small portion of failure, it still needs to be addressed. We always need to constantly try to improve the process, improve the technology, and improve the patient experience. So just as some examples here, more than 2,000 device-related deaths and more than 200,000 reports of device-related injuries and malfunctions are reported to the FDA every year in general. Many of the adverse events are blamed on the user. Like, oh, the user, they didn't do this correctly or follow these instructions correctly. But still, even as engineers and designers, we have a responsibility to address any challenges that the user faces. If they're having a really difficult time following the instructions and not remembering some type of portion about an electrical device, then we need to start addressing that and see how we can fix that and go a different route maybe with the design. More recalls have been happening, so there's more device recalls, and that's not paralleled by an increase to how many products are going to market. So obviously an issue there. And medical equipment and breakage and failure was found to be the most common precursor event for medical device-related incidents. And then 22.5 of medical device-related incidents occurred intraoperatively in one particular study. Okay. I want to cover a lot, so sorry if I fly. So some surgical device examples. We'll do a couple here. So for the stapler, we have, let's say we're going in and we're going to staple some stomach. We're going to go in, we're going through a small incision, remember? And we have all of the stapling mechanism, it's happening inside. You're just handling it from the outside of the patient. Let's say your device gets stuck and it's clamped down, closed on tissue. The jaws are supposed to release, but in many times, it will get stuck for whatever reason, whether it's a mechanical reason, all these types of things. What they will have to do is make another incision and either go in with another device right next to it and cut additional tissue off in order to get that malfunctioning device out and off, or they will have to take, it could be literally sutures. What if they don't have a device? What if they don't have an extra device? Depending on what country you're in, you may have to bring your own device to your surgery, which I know that sounds crazy, but I did some research in other areas, and they'll be like, you need this and this. So if you didn't bring an extra device, or your hospital doesn't have one on hand, or whatever insurance issues are going on, they might have to go in and actually suture it and manually cut that device out. You're losing more tissue, you've got more bleeding risk, infection risk, and things like that. So that's just one example of what I actually saw quite a bit when I was assessing failure modes of these devices. So here we go, big picture. The rate of adverse events, it has suggested to be relatively low. Yet any incident is reason for concern given the potential catastrophic consequences like I just mentioned. And there are worse ones that I saw, much worse. That's just one example of many. Therefore, what knowledge tool, technique, or tool can we develop as engineers to assist in preventing adverse event outcomes associated with surgical devices? So that was my main driving question for my work and how, I mean, even at the time, I didn't even know what I was going to do yet, but that was my big overall, big picture driving question. So we'll start with some background. In general, there's also a knowledge gap for surgeons. Surgeons, they're not aware of everything about these devices, which when you really think about that, that's kind of frightening. You know, they are not aware of failures and, you know, even, what's the word? Like reactive mechanisms. When you have a failure, what are you going to do about it? What do I do next? How do I fix this? That type of thing. Especially, this is very prevalent in energy-based devices. They don't understand, in many cases, the basics of electricity. So if they're having issues, you know, such as a stray current, or let's say a portion of the device that has insulation, if that gets somehow nicked or cut and it's no longer insulated, so then you've got current traveling elsewhere. In many cases, patient gets burned because you've got uncontrolled current when these issues happen. But they don't know. They don't understand what parts are insulated, what is insulation, and these types of things. So definitely needs to be addressed. Let me get to so the FDA Manufacturer and User Device Experience Database, that was, I spent many, many days running through that. What this is a medical device reporting database. So a user has an issue and they can go in there and explain it, talk about which device it was, what brand, what type of procedure it was used on, and submit it to that. So that is how I had access to figuring out what was going on out there with different types of devices. There have been failure mode studies similar to part of my work. However, these would look at broad ranges of devices, so just energy as a whole. So energy devices as a whole versus this specific brand, or this one that specifically utilizes bipolar or ultrasonic vibrations and digging deeper into a specific area. And also, there is no investigation into specific design-related factors that are affecting the failures. So it's kind of taking someone with more just clinical medical background, many times these are in surgical journals versus any type of design or engineering journal, and they're just assessing the failures, but they can't trace it back to any type of design issue. And also, no further analysis of the outcomes is provided in those studies. So, okay, we've got a bunch of failures, well, what past that? You know, we know what they are, but what's really going on? You know, how severe are they? Is that one worse than that one? Does that one happen in that procedure more than this type of procedure? So there's a lot more diving deeper that you can do in this particular area, which, again, good for us, right? Anyone interested in going the dissertation route? So my long-term goal was to facilitate intraoperative safety and prevent patient injury and death caused by adverse events associated with these type of devices. In particular, I had 2 study goals. One was to characterize the design attributes, the failure modes, and adverse events associated with minimally invasive surgical devices, and 2, to describe the relationship between the design complexity of these devices and the severity of their adverse event outcomes. So it's taking the failure modes, assessing the outcomes of them, and actually applying a severity score to them so we can start assessing them in a way that's going to be beneficial and to look at relationships. These are my very specific aims. So that's what, I'm sure you guys are at least a little bit familiar. You have an overall goal, and then you have very specific tasks that you are saying you are going to execute in order to reach that goal, or in order to solve your research problem. So my first one was to describe the failure modes associated with these 2 device types, the endoscopic staplers and the tissue sealers, the energy-based tissue sealers. Second, I was going to describe the severity of the adverse event outcomes that were associated with those failure modes. Third was to bring in the design element and to actually try to characterize the design and the complexity of a device in some way. Complexity is very broad, and sometimes it's hard to even think about. Design theory kind of gets a little tricky. It's just odd, we talk about complexity you can talk about complexity of a process, a product, a problem. It's a very kind of abstract idea. So we really had to narrow in. I say we all the time. I had to narrow in. I had to narrow in on what definition I was going to use to apply to my research. And then the overall goal was to describe the relationship. So my hypothesis was that as the device design complexity increased, I was hypothesizing that the severity of the adverse event outcomes would also increase. And the last one was to develop a tool to predict the likelihood of severe adverse events associated with minimally invasive surgical devices that was based on complexity. So if I could say, this device has this complexity score, what am I looking at severity-wise? Is there a way I can predict the severity of the outcomes of that? Keep in mind, unfortunately, I wasn't able to get to that one. I didn't have enough statistical power for that. So there you go. There's another opportunity for you. So now I'll give you a very brief overview of the methods before we get into each aim there. This is in general medical device design, so you guys might be familiar with that general area. And failure analysis, in particular, a new approach to failure analysis. So this is the first time that anything in this area has been looked at from a device design complexity standpoint. And then I'm also assessing the adverse events to see the relationship there. This is a little bit more in depth. So here's very bluntly the 2 sides, right? So one side, totally mechanical engineering, design theory, looking at design complexity, in particular, a method to quantify design complexity, and then to apply it to these device types, and then have a resulting complexity score for each one. And then on the other side, we're looking at more in surgery, intraoperative surgical outcomes, and assessing the failure modes and the severity of the outcomes associated with those failure modes. I had to have a type of grading method. There is no specific grading method that exists that I could apply directly and flawlessly to these outcomes. So I found one. It was the common terminology criteria for adverse events, and their general 1 to 5 grading scale that they provided was applicable. I was able to apply it very specifically to these outcomes. Not perfectly, but it worked the best out of all the options that were there. And here it is specifically. So you got 1 through 5. 1 is mild, 2 is moderate, 3 is severe or medically significant, 4 life-threatening, and 5 a death related to the adverse event outcome. Let's touch on some mechanical engineering things here. I also looked at the function of these devices, so we'll get into that a little more. But a functional model is something very useful in engineering design. You can take, let's say you had a list of customer needs, right? You have a list and you need to develop a product that's going to fulfill these needs. Many times in our head, we always think about things that exist already. That can be really beneficial, but it can also really hinder your creativity. So if you take a functional model, it's just a very general representation for a designer to see the functions that need to be executed without it actually taking on any particular form. So then you can have more creativity in your design. So just as part of the design theory area, I also looked into that. Complexity. Again, very kind of, complexity is a complex area. So consideration of an objective measure of complexity. This aids systematic design elements and enables quantitative comparisons of design solutions. So like I said, this could be applied to a design problem, a process, or a product. Any of those. There are many different methods that exist. However, for a design product in particular, there were only a couple of options that I had, and people, other research that was done to actually develop methods to quantify product complexity based on some measure of it. In particular, the one that I ended up going with was connectivity. So the connectivity of the devices. So all of the parts within there, mapping the connectivity and deriving a complexity score based on that. This is what the connectivity algorithm kind of as mapped out what it does. It's really, overall, it's measuring the decomposability of a device, of a product. So how difficult is it to take it apart type of thing with all of the connections that the components have. That's really just a good overview of that. And this graph on the right, that is what you would have to make for your product. So you've got all your components on one side and the relationships between them on the other side. If you have a product with 100 parts, you won't be able to read that thing when you're done. So luckily, the actual developers of the connectivity algorithm, they had a MATLAB program for me. Thank goodness. Here were the actual specific devices. So these are actual pictures of the devices that I took apart. These were the two staplers. So I took two different brands, two competing brands here. And they work in a very similar fashion. The one at the top, the Covidian, you can't see very well, but in the middle of the shaft, there's actually a break where that distal portion with the jaw, that is what is considered a reload. So every time you fire the device, you have to actually disconnect that and attach a whole new piece. Whereas down here for this Ethicon device, every time you fire the device in the same patient, you can use this device itself. The only thing that is changed out is a stapling cartridge that you insert down in that rectangle portion of the bottom jaw. So they operate in different ways, but they're executing the same function. Here are the tissue sealing devices. The one at the top, that's the one I was telling you about, the Olympus Thunderbeat. That integrates bipolar and ultrasonic technology in the same device. Whereas the one at the bottom, this Ethicon Harmonic Ace, is purely ultrasonic technology. So just the vibrations to create the mechanical to the thermal energy to heat, seal, or cut. Oh, another note. So how you get a hold of these devices, I was limited because I had to get what was available on eBay. Yes, believe it or not. Interesting that you can buy these on eBay, right? So specific aim 1, I'll give you the general methods and results from this portion. This is to describe the failure modes associated with all 4 of those devices I was telling you about. So that meant digging deep into the device database I was telling you about that the FDA has. So anyone can have access to this. You can go here at any time and you can search for specific devices and also recalls from the FDA. You can also get recalls. So I wanted to look at the failure modes from this database to see what was happening. But from my background research, it kept saying, oh, it's the user's fault. Oh, the user operated it incorrectly. So then I also pulled the recalls so I could see what was happening from a functional and design standpoint as well, what malfunctionings were happening that were device-based. Here's an example of the results for one device for this section. So I had 4 of these tables. I broke it up into phase of operation. So these phases are very specific to endoscopic staplers. So I had 2 tables just like this for the 2 different staplers. And then within those, very specific failure modes within each phase of operation. So really what I'm seeing is a relative frequency to the total sample that I pull, just seeing which ones are the most common from the group. So this shows you very clearly where the most issues are happening in terms of their phase of operation, it's the firing phase, but that's rather intuitive. That is the portion of operation where you're cutting and stapling. Lots of issues can happen at that time. So that's the majority there. And then again, removal. So the example I gave you was where you couldn't remove the device. So that would fall in that category. After you cut and staple, it won't release, it won't open back up from the tissue. And the next one is staple line. So actual issues with the staple line after it's fired. Whether the staples didn't hold that seal together, or whatever the case. It could have even failed post-operatively. So this was pulling the most common ones. So again, of the phase, the most common were firing, removing the device, and the resulting staple line of the firing. And then within those, the issues as well. So failure to release, a leak post-op, and as well as malformed staples is a big one too. So you're firing the device, and it's not resulting in those nice B shapes. It's totally off and is not going to secure the tissue. So here's the same graph type with the phases of operation, but for the energy-based tissue sealers. They have different phases of operation because they're executing a similar task, but in a much different fashion. So you have activation. That's the portion where you're actually applying heat and you're sealing or cutting tissue or a vessel, whatever the application. And post-op is what happens with that seal after it has been created. And then transition is anything in between. And you may think transition, that's an odd one. But think about this. You have a device that's getting really hot at the end, at the distal tip, where it's inside the body. Sometimes your cameras, they don't show you your whole view of the whole body inside when you're doing an endoscopic procedure. So you can take that device out, and in many cases, I saw so many times, that residual heat of the tip, it will hit the bowel. So if you burn a hole through the bowel, then you have leakage, then you have infection. And in other cases, they would actually burn the inside, but up in your stomach. Yeah, because it's just handling of the device and accidentally hitting something that shouldn't be hit with heat. So these were the very specific ones that were the most common of the entire group. So you have activation, there were issues, actually a lot of broken device issues, and that's a difficult one because sometimes they'll push that back on the user. Oh, you applied it to tissue that was too thick. You know, we instruct that it only can be this many millimeters or whatever the case. Just a lot of different specifics, a lot of variables that surgeons have to consider. I mean, they're already in a high pressure situation. Let's just add a whole bunch of huge list of specifics that they have to follow in every situation. Everything's not always ideal. And as soon as you open up a patient, that tissue might not look how you thought, especially if it's diseased or there's an issue going on that you didn't expect. Okay. So overall, this means that there were user and device-based failures happening. This was also present in the recalls that I assessed as well. There were many recalls for endoscopic staplers. So again, to specific aim 2, this one is where I was just taking those exact same failure modes, but looking at the specific outcomes that happen from the failure and applying that severity grading method. So we may have, the failure where it's the one I told you about, where maybe you hit the bowel with the residual heated tip. That could cause a 3, 4, or 5, which means medically significant or worse. Or if you just simply poke one little tissue and it doesn't really, they don't have to do anything about it, like, oh, it's fine, shouldn't have done that, but it'll heal fine, that could be a 2. So just to see, we may know what these failures are, but what's the range of what's actually happening? What's the outcomes from these? So here's a sample of the table for one device. Again, so I had to do this for all 4 of them, but I had to go through and assess the severity for each instance of each failure. And so that's just the 1 to 5 grading scale, and then average those out per failure mode. This is looking at the most severe ones for the staplers. And this is a good example. So failure to deploy staples at all or on both sides. That was one of the top 3 most severe, as well as one of the most frequent that occurred from the sample. So you don't want to just look at one thing or the other. If we just look at frequency, it's not going to help us as much as looking at severity and frequency. These can tell us staple line leak post-op, it only happened 6.3% of all the failures that I assessed, but it was one of the most severe when it does happen. And same thing here for the energy-based tissue sealers. Therefore, overall from this aim, so I'm giving you guys really just high-level overview. I don't want to bore you too much with all of the results. But assessing both frequency and the severity of the outcomes is really what the user and manufacturer needs. They need a more comprehensive outlook of what's going on. So now I'll get into the design component of the work, and that was characterizing the complexity. So the functional models, we'll touch on those, develop those for each of the device types. So the function for an endoscopic stapler and function for the energy-based tissue sealer. And in order to apply the connectivity algorithm, I had to map the components. A really easy way to map your components and utilize it and see how your connections are, how many connections you have, is to make a design structure matrix, which that's just a sample of it. So just a few parts, just like a subset. But what it does is it maps connectivity. So the knife is connected to the anvil, like that type of thing. So then you have that. So as I took apart all the devices, I was just creating a map of the connectivity that is actually utilized in the connectivity algorithm to determine a complexity score. Here's the functional model. This is for the endoscopic staplers. These in particular, because the two that I assessed were purely mechanical. So this only shows mechanical things. So import hand, import tissue, import staples. And then you have human energy converted to mechanical energy, and then that's the main driver. Our two main functions are to secure and separate tissue. So the interesting thing is that is the exact same two main functions that the tissue sealer has. These are the energy-based tissue sealers that seal the vessels. Because when you think about it, you're doing the same thing. You're just wanting to cut tissue in some fashion and secure it. They do the same thing, but in complete different ways, and they're for complete different applications. So to have a functional model is really useful to get more high-level overview of your customer requirements. What's your main thing you're trying to achieve? And look at the two different diverse options that were designed just depending on the application. So you can see here we actually had to import electrical energy from a power source. They're connected to a generator in order to generate the power, and that is what's utilized, as well as thermal energy to create a seal. Here's just some exploded views, because it's cool. So that's what they look like just taken apart. These are the tissue sealers and the staplers. So you can see the big difference is that the one at the top, I think that had 38 components. The one at the bottom had 89 components. So they're doing the same thing, just really big difference in how they execute that function. Here were the results. So the two staplers are at the top, and then the tissue sealers are at the bottom. These are the complexity scores at the top based on connectivity. So that was the actual device complexity scores. And the stapler had the highest, the one with the 89 components. Pretty intuitive there. And the functional model, I also applied the algorithm to the functional model with the connectivity of the function. So all those little boxes you saw, how they're connected to the other ones. So that's more of like a functional complexity assessment. For time's sake, overall, what I'm saying is that the stapler that had a ton of components, that had more of a modular design, where the entire distal end of that device could be taken off and a new one could be put on. That modular feature is a big reason for why it has so many more components. But yet to a surgeon, that might be viewed as a benefit because each time they get a new distal portion for each new firing that they do within the same patient. So they may see that as a benefit, may not. The Thunderbeat, the one that integrates, the tissue sealer that integrates ultrasonic and bipolar technology, that one was more complex than the device that only utilized the ultrasonic technology. Also fairly intuitive, it's got more going on, right? The thing is that device with both technologies, there are studies that have shown that it is actually parallel, if not even better, in performance. So many times complexity is viewed as a bad thing, just in general. It's viewed as a hindrance, right? And it makes it difficult to go back to redesign. Just lots of hindering aspects have been linked to complexity in the design studies. But here, I just say with caution, maybe your design complexity should be weighed, provided the benefits that it may provide for the application. So 4 and 5 were to actually look at the relationship. So I'm taking all that I did from the first two specific aims with the severities of the adverse event outcomes, and my goal was to look at that side by side with complexity of each device. So I've got the complexity score, and I've got the average outcome severity of the failures that was happening with that device. And then again, 5 was to develop the predictive tool. Still an opportunity out there. So what I did is I used ordinal regression to attempt to do that. And that would mean that my independent variable was complexity, and my dependent variable was the outcome severity. So that's my ordinal. So when you have a scale, 1 to 5, it's an ordinal variable. That's why you have to use ordinal regression. So here's in general just the complexity score from lowest to highest, and you can see that the average outcome severity did not increase linearly with that, unfortunately. But it's okay, because I was only able to look at 4 devices due to, well, budget is a huge one. Go ahead and prep you for that if you want to get into research. Budget is a big one, as well as resources to obtain them. I was limited by what was available on eBay, because these companies don't just give, they don't just give them out, and they charge way more to actual hospitals. They're just outrageous costs. And these were the functional ones, so the tissue sealer actually ended up to be more functionally complex, yet resulted in overall lower outcome severity. So this is just saying that I didn't have enough samples. So my statistical conclusions, I have a lot more statistical stuff, of course, in my dissertation, but this is high-level overview. But just keep in mind that sometimes you have to have pilot data. My study kind of serves as a pilot study, because when I would meet with the statistician, he's like, well, has this been done before? Can we use that as pilot data? I'm like, hasn't been done. So we kind of just had to go with the flow and try to back out a power analysis. So this would actually be useful for going forward in order to then, in the beginning of your project, plan your budget. So a summary, overall, is that we need methods that are going to integrate domains. We have to start working together with actual surgeons. I mean, my dream for this work would have been to go into actual procedures and watch the use of the devices and assess as many failures as possible. Probably would take me a really long time, and it's extremely difficult to get access to that kind of stuff, unfortunately, but that would be the perfect scenario, is to see it for yourself and to assess it as it actually happens. Because what happened for me, and that's a limitation of the study that I'll get into, but the event descriptions are not as good as us as engineers would want. You have a surgeon coming out of a procedure and saying, this device did blah, 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 blah. It failed and did that. Then you probably have someone at a desk typing that in, entering the actual reports. So a lot of information is not conveyed that we need to really dig deeper and figure out what's going on. We're like, well, what component failed? Well, what did that do? You don't get as much as you wish you could. So, oh yeah, I already touched on that. So my limitations, there were a lot of limitations for each study. These are the main ones. So as I mentioned, insufficient event descriptions. If they're not explaining something correctly in their medical report, then obviously that will lead to incorrect conclusions on my part on what failure mode it was and what the outcome was as well. The connectivity algorithm, you may be already thinking this. So that is a complexity score based on connectivity. I'm looking at the parts and how they're connected, and well, where's other aspects of this? Those energy devices, they use an external generator that they have to be plugged into. Electrical features could bring in a whole different look on complexity. So this particular algorithm that was applied did not include those. Another area that could be expanded. Again, not enough devices available. Future work would involve a power analysis to determine the budget, but again, this type of thing could actually serve as a pilot data for a power analysis going forward. Future work. So here you go, listen up. If you're interested in this area, there are so many things that are left to do. And yes, oh, if you have to get to a class, please, yes. Especially if it's a long walk, yeah. So just in general, you need to look at the system as a whole, right? You need to look at more than just the device. You also have user issues. So you've got instructions of use that are too complex. We could assess multiple aspects of a procedural setting, so not just one. So there's many different areas of expansion in this topic. And I think that's pretty good, because these were my last couple slides. So if you have any questions, you can probably follow up. Like if you were really interested in this area, my advisor was Dr. Gina Bertacci. My other advisor, he was in the mechanical department, but he's in Florida now, so he's no longer here. But the Bertaccis, they guided me through a lot of it. So if you're interested, they would be a great source. Do y'all have any questions for those who didn't have to go to class? Yeah.
So are these devices, are they typically reused from patient to patient, or are they disposed? I mean, I know it's surprising sometimes the things they throw away.
They dispose mostly of this.
Okay.
The only one that they could actually keep something of was the one where the distal portion can twist off, so they can reuse that handle, but only for a certain amount of time. All of those other ones, immediately after the patient's use, disposed of. Yeah?
I was just wondering if you received any support, like financial or verbal, from the FDA, since you were kind of building on their previous research?
Unfortunately, no. But maybe in the future, though, because it's kind of, when you're getting started in a topic but there's nothing done before it, you're kind of navigating as you go, just kind of going for it. But if you already know early that that's what you're interested in, it would be really wise to pursue that opportunity before you even get going. Yeah, because then they could approve your topic, because of course you have to submit some type of proposal, I'm sure, and then they would be like, yeah, that's good to go. So the earlier the better, but I bet that's possible. Mm-hmm. Yeah.
Will startup company focus on this device?
Actually, the startup company, I started that while I was doing the doctorate program, but that's actually a completely different area.
Yes.
It is actually, I use chemistry every day. It is in the cannabis industry, and I work with the hemp plant. So that is basically the same thing as marijuana, except government says that the THC level, so THC is the psychoactive component of the cannabis plant, it has to be below 0.3%. So that would do nothing to you, People, if they, took some off the farmer's fields, nothing's going to happen to them. But what I do is I extract the cannabinoids from that. So there's a lot of research going on with CBD, CBG, CBN. These are all cannabinoids that the cannabis plant contains. And I can't make any claims, but lots of medicinal purposes. So I just develop products from the extract things.
Mm-hmm. You actually tried to associate the complexity with the severity of adverse events. Did you look at just the frequency of adverse events related to whether it was related to complexity? The reason I'm asking is, for example, if you have redundant systems, that will increase complexity, but that will also increase reliability, and it would reduce both the frequency and the severity of adverse events. So it depends on what type of complexity why the complexity is in there in the first place.
Yes, exactly. And so that's kind of what I saw, is that all of these studies that I had read is reduce complexity, get rid of complexity, whatever kind of complexity is, we don't want complexity. But in certain cases, if that is providing a feature that is going to decrease adverse events in general, then it would be a necessary complexity. So it's actually a whole different kind of perspective on it. Because in the design world, it hasn't really been applied to a situation like this. Right now, there are just researchers looking at how do we quantify this thing? How do we quantify the complexity of that? And they're trying to come up with methods to give a score that could be compared among products, processes, and things like that. But as far as applications and actually applying it and looking at something else going on with the products and how they're applied, that had not been done yet. So I think there's a lot of opportunity there to assess more than just one thing at once.
So the other thing that medical device companies do is they do validation verification testing, where they go through, like 1 million sutures and things like that.
Right.
And so looking at those tests, I think would give you a better indication of reliability because the FDA has, certain reliability standards that need to be met.
Right.
And I'm coming from, mechanical circulatory support devices or valves. They have to go through X number of millions of cycles before you start having these fractures or
Exactly.
before it fails.
Yeah.
So when you do those failure analysis and you determine that it's below a certain risk level, what is this complexity analysis, given that it doesn't correlate perfectly, or in fact it's not correlated as far as you can tell?
Right.
How will that supplant or supplement the validation verification testing?
Well, I would have to first prove that, you mean if I actually was able to prove that there was a relationship in order to then aid those types of things?
No, how will your analysis how would your analysis be useful when, in addition to the validation verification testing that they are doing, to determine, that you have one failure in a million devices, right? So, do you think, given that you don't have a correlation at this juncture, maybe even if you found the correlation, maybe yes, you can go and try and do the design aspects, reduce complexity or increase complexity, reliability,
right, whichever
some
way.
mixture.
Yeah.
And try and, before you go to validation verification testing, where before you go to design freeze, you can improve that process.
Right.
But given that the correlation is not there, how do you see it supplementing the validation verification testing?
Sure. So, I think the biggest thing from my perspective is that when a device is fired over and over and over in the perfect condition, typically, so when I was at Ethicon, right, they're firing a device on nice vessels, perfect vessels from pig tissue, or some other animal. But this is looking at what's actually happening in an instance where it's not a perfect world. So we're looking at the failures that happen in practice where tissue's not perfect, where you don't know what kind of tissue you're going to encounter going in, and what can be backed out of that. So it's understanding the user's perspective. Because you can do those type of tests in a perfect condition, in a perfect environment, and it's still not going to be always representative of what can happen to a device if it's fired on tissue that was not used in all of its testing for approval with the FDA, those type of things. So I think it's more of a real world application and looking at the complexity of not just a device itself, because what I took from my work is to look at something as a whole. It's not just one simple thing like, oh, this device can do this many times. It's also, what's the user's understanding of how these devices can be used? So not just looking at one component of it, I guess would be. So not even just looking at verification testing, but even instructions for use. Can these surgeons understand how to properly use it? In many cases, it was that they were firing on tissue that it wasn't meant for. And so it's still going to fail, but as engineers, we can't just tell them, hey, only fire this device on this one bit of tissue in this type of condition. They open up the body, that device is all they have, might not always be perfect. So I think, your question in how to actually apply this, it's not directly applicable to those specific tests, but I think in general, looking at it used in a real world situation where you've got users who might be misusing it and trying to fail-safe some of those things and bringing in complexity of that. If we add fail-safe methods like lockout mechanisms and making sure that a surgeon can't fire a device without a cartridge in there, so if they just cut without even having the stapling cartridge there. If we can put in fail-safe things, if that adds to complexity, maybe it, so be it, maybe in this case, it's good and contradicts a lot of the complexity research that's done already. If that makes sense.
No,
yeah, because I spent so many months on this, so I'm just like, oh, well, this and that, but I know it's not as clear-cut, which in many cases, your work won't always be so clear-cut. Like, I wish I could have proved my hypothesis, right? We always wish. But just the contributing work into even starting to assess more of this system as a whole and looking at not just what type of failure modes happen, but what actually happens from them and going from there. Anything else? Yeah?
In clinical research, there is a term called risk that combines the frequency and severity into one term. This is called risk. Did you study this?
No, did not look specifically into that. But sounds applicable though.
I tried multiplying those two in my head.
Yeah, multiplying them.
Yeah. So
they're
when you put the
equal.
tables, it didn't seem to correlate.
Right.
You can
Right.
verify that.
Yeah.
So, don't you think when the complexity of so using, for example, two sources of energy, for example, these kind of devices will be used in tissue where the severity of an adverse event would be multiplied. So it's kind of a confounding variable of a sort. So was there a method of controlling for this?
In actual application?
Yeah.
So you're saying
we
if-
were collecting this data.
Mm-hmm.
So you would, if they're using this tissue, for example, with, I don't know, the aorta, for example, as opposed to distal, just a small artery, for example. So if they're going to use a more complex device, I suppose, so if an adverse event would happen, it would have more severe outcomes. That's what I mean.
Right, and that's actually a perfect way of thinking about it. So my work was focused on looking at the failure modes, looking at the adverse events, and then literally in my future work statement, it is to actually go in and look at procedure-specific outcomes. So let's say we're using this device, and it has these failure modes and these severity outcomes. Now let's break it up further and sort it further into procedure type. Whether that's just a gastric procedure or more thoracic, where you would seemingly be more risky, that type of thing. So that would be definitely a next step. But that is where it goes back to looking at the system as a whole. So let's not just look at failure modes. So we're going further than that. We're going to also look at severity of the outcomes, but then go further than that and break up severity and what's going on per procedure type. Because there's so many things that are affected based on procedure type, whether that's your visibility in that particular region of the body, or like you said, what type of structures is it actually being fired upon? Yeah. No, that's an excellent point. So definitely a point for further investigation. Anyone in here thinking about doing a PhD? Well, I'll tell you this. I did not think I was going to do a PhD whatsoever. I was in my master's, and there was a professor in the mechanical engineering department, and he's no longer here. But I worked in the mechanical engineering lab as a teaching assistant, so I was there all the time. Every time he would pass by, he would bother me about doing a PhD. He's like, "Maria, you want to do a PhD?" And I'd be like, "No, get away from me." Like, don't even think about it. But the more I thought about it, and the more I looked into the opportunities, for me, it was a fit. For me, I was glad I went that route. Never thought I would do it. Never thought. I was like, I'm going to go into industry and have a medical device engineering job. Like, I was just so set on that. So don't always think in one narrow path. You might go a different direction. It might be worth it. If I never would have gone the doctorate, I never would have had the extra time to start a company. So it's just weighing your options, and especially if you have a topic of interest and you enjoy researching things and developing things that haven't been done, or looking at something in a new way, if that is something that you just happen to have a skill at, because that is a skill to a certain extent, and also a skill to develop, to be able to think in that type of direction versus just industry position. But I would say consider it, think about it, especially if you have an advisor. So finding an advisor, that's a crucial part of it. My main advisor, his whole area was the design theory stuff. I brought in the mechanical. I told him, I said, here's the deal. I said, I did my co-ops here. I love this work. I want to work in medical devices. And I told him, I said, I won't do a PhD unless we can apply your work to what I like. You don't want to be, working on your dissertation for months and months and months, and years in some cases, and you don't like it. That's what I told him. I said, I have to really enjoy the topic. So luckily, I was able to take the design theory world, what he was doing, my main advisor, and apply it into medical devices. And then, but the Bertacci's came in, Dr. Bertacci came in. He ended up going to a university in Florida. So he just wasn't here anymore, unfortunately. And so then they kind of took me on, which their very knowledgeable. I mean, I'm sure you guys are a little bit aware of their research areas. It's not in this particular area, but their injury, looking at child falls and things like that, so actual injury biomechanics. So I know Dr. Bertacci will actually look at court cases and things to determine whether a child, their injury really was from a fall or whether it was some form of child abuse. So looking at bruising and things like that. So really interesting stuff. And that's not the only thing that they do, but really great opportunities I know in their research lab, because I spent a lot of time in her lab. Anything else?
Any more question?
Good?
Okay, thank you for the